Night on the moon is cold and dark. For 14 Earth days, the solar panels sleep. For 14 Earth days, the batteries groan under the load, but the base stays bright. Life support hums. Labs stay warm. Rovers are charged and ready. It's a miracle. No, it's not. It's engineering. And tonight, we're building the power plant that makes off-world life possible. We could use giant solar arrays, but those track the sun and sometimes face dust storms. We could use big batteries, but charging takes sunlight, which is scarce on Mars and absent on the moon. And we need power when the sun is down. We need power on nights and weekends. We need power when no one is looking. So we build plants, nuclear plants. We'll take the heat from splitting atoms and turn it into watts. Quietly, steadily, dependably, at the edge of human exploration, a tiny miracle. That's our fission reactor playlist. Let's get to work. First question, why fission? Space is a terrible place for power plants. On Earth, we dam rivers or burn forests. But off-world, we have nothing but the raw materials we bring with us. So fission brings three things: high energy, density, all-weather reliability, and compact mass. A coffee mug of fuel, figuratively speaking, can run a habitat for years. It's not flashy, it's not fragile, it's just dependable watts when everything else is asleep. And those steady watts buy you a lot. Heat when the regolith tries to freeze your pipes, air that stays breathable, water recycled, lights on, labs running through the long night, rovers charging while the dust settles, ISRU cooking oxygen out of moon rock, comms dishes beaming home. Reliability in space isn't a luxury, it's life support. And that's why we send them to the edge of the solar system. Now, split that family into two. Space reactors come in two flavors: surface power and propulsion. First, surface fission power. We land a small plant on the moon or Mars. It feeds power to nearby habitats, drills, and comms. It might seem obvious, but that's because it's been done. In the 1960s, NASA ran 30 years of nuclear power on the moon, or at least they tried to. Those reactors never left Earth's gravity, thanks to the Apollo program's cancellation, but their descendants are alive and well on Earth. We've been using fission reactors for 65 years to power remote camps and research stations. They're rugged, reliable, and they last for decades. And soon, we'll try it again. This time for real. Second, propulsion. Nuclear electric propulsion, or NEP, uses a reactor to generate electricity, which runs ion or Hall thrusters. These produce a tiny but relentless thrust that stacks up over months or years, giving huge delta V, perfect for heavy cargo ships, deep space probes, or crewed missions with tight turnaround times. It's not flashy thrust. It's perfect for when no one is watching. And second cousin once removed. Nuclear thermal propulsion. Skip the generator and pump hydrogen directly through the core. Heat it white hot and fire it out a nozzle. High thrust, higher efficiency than chemical rockets. Same heart, different plumbing. But both of those flavors share 5 boxes inside. Open the lid and most concepts rhyme. 5 boxes, 1 fuel. A uranium alloy or ceramic that keeps its shape when it's really hot and really irradiated. 2 control, neutron absorbers or rotating drums tune the chain reaction up or down. 3 coolant, liquid metal or gas that carts heat out of the core without boiling away. For power conversion, turn heat into volts. Stirling pistons, Brayton microturbines, or solid-state thermoelectrics, and 5 radiators. No air in space, so you glow heat away. Big light panels fed by heat pipes. Set your power ceiling, fuel, control, coolant, conversion, radiators. Master these 5, and the rest is packaging. And let's start with fuel. That's the core's backbone. It must shrug off heat cycles, radiation damage, and launch vibrations. Tiny grains of fuel are sealed in cladding, stacked into pins or pucks. Geometry matters for neutron life. Now control is about reactivity. How many neutrons survive to make the next fission? Rotating drums are elegantly simple. Each segment is half reflective, half absorbing. Turn the bright side toward the core. More neutrons. Turn the dark side. Few moving parts. Predictable behavior. Next, coolant. It's easy to carry heat away. It's harder to turn that heat into electricity. Stirling, a sealed piston shuttles gas back and forth, driving a generator. Great at small scales. Mechanically simple, surprisingly efficient. Closed Brayton. A tiny turbine spins in a sealed loop. Think jet engine in miniature. Efficient from kilowatts to tens of kilowatts. Thermoelectrics, no moving parts. Hot side, cold side, electrons do the rest. Rugged and quiet, but you trade efficiency for simplicity. Pick the converter that fits the job, and the maintenance you can actually do off-world in radiators. In vacuum, you can't blow on a heat sink. You radiate energy leaves as light, and that scales as temperature to the 4th power. Heat pipes move heat, using phase change liquid out, vapor back. No pumps, no fuss. They spread the core's heat into wide featherweight panels. Run radiators hotter, and you can shrink them, but materials work harder. Run them cooler, and they get big but gentler on hardware. It's a geometry versus materials trade you can see from orbit. How big are we talking? The bigger the plant, the more power you get, but also the heavier it gets. At some point, you're launching more reactor than payload, so you pick a sweet spot based on mission needs and bus capabilities. Take a look at history. Our first US fission reactor in orbit, SNAP-10A, a few hundred watts of electricity, weeks of operation before a non-nuclear fault ended the test. Small, real, a proof that the basics work above the atmosphere. Soviet heritage, across the ocean. The Soviets flew dozens of compact reactors. Later came Topaz thermionic converters sipping heat straight into electricity. In the 90s, the US tested Topaz-2 on the ground to learn from that hardware. Different approaches, same goal. Reliable space watts, a hard lesson. Cosmos 954. Not every chapter is clean. In 1978, Cosmos 954 reinterred and scattered debris over Canada. The response, Operation Morning Light, was massive. Modern designs plan end of life from day one. Stable orbits, safe disposal, or on-surface isolation. Stewardship is part of the engineering. Then a hard-won comeback. In the 2010s, NASA and the Air Force followed through on kill the power. A compact core, heat pipes, and Stirling converters. Run hot on a test stand. The crusty experiment pushed through startup, steady power, and transients. It wasn't a paper study. It was metal, heat, and measured margins. What did we learn? Small reactors can be simple and predictable. Perfect for the first bases that need more than an RTG but less than a city. That's when you break out the fission playbook. Deploy a small plant, plug it in, and watch the lights come on. Now let's talk safety. Calmly. We know that nuclear power scares people, so let's dive into why these reactors are safe. First, cold launch. The reactor ship's subcritical. No chain reaction on the pad. Start in place only after you reach orbit or the surface. Second, passive bias. Geometry and materials that nudge the system safe if it heats up. If something drifts, it drifts toward shutdown, not runaway. Third, shield plus distance. Dense shielding right by the core and the reactor set back from where people live. On the moon or Mars, you can pile regolith berms into the design.